Welcome back. In this session, we are going to dive deeper into arrays. As we continue to explore arrays, one key feature that makes them so efficient is their use of contiguous memory allocation. To understand the efficiency of arrays, it's important to note that they use contiguous blocks of memory, meaning all elements are stored in a single, continuous section of memory. This layout provides efficient indexing and constant time access to elements. Accessing an element involves a straightforward calculation based on the element's index. This calculation allows for quick retrieval and enhanced cache performance. Efficient memory usage and fast access make arrays a powerful tool for handling data in programming. One reason for the zero-based index in arrays is closely related to their implementation in memory. The base address of the array is used as the starting point. The index directly corresponds to the position offset from this base address. This indexing approach simplifies the calculation and enhances the efficiency of accessing elements in memory. Arrays are also closely related to pointers. In languages like C and C++, an array name represents the memory address of the first element. This means that the array name is essentially a pointer to that element. This relationship allows for efficient memory access and manipulation, further enhancing the performance of operations involving arrays. However, this efficiency comes with certain trade-offs when performing specific operations, such as insertion. Insertion involves adding a new element at a specific index. To insert an element, there are two distinct cases. When the array is not full, then we shift all the elements one position right starting from the last element in the array until the index where we want to insert the element. This process makes sure we don't lose any element. Then we enter the new element in the desired index. When the array is already full and we want to insert, then starting from the second last element in the array, we move everything to one position right until the index where we want to insert the element. Then we insert the new element in the desired order position. In such cases, we lose the very last element. When inserting an element at the beginning of an array that is at index 0, all existing elements must be shifted one position to the right to make space. For an array of size n, this involves moving all n-1 elements, assuming that the array is full. The process requires a loop that runs n-1 times, with each iteration moving a single element. This shifting operation leads to a time complexity of big O of n in the worst case. Deletion is the process of removing an element from a specific index. After removing the element, subsequent elements need to be shifted to fill the gap left by the removed element. Deleting an element from an array has a time complexity of big O of n, because after removing the element, all subsequent elements must be shifted one position to the left to fill the gap. For an array of size n, this means moving up to n-1 elements. The process requires a loop that runs n-1 times, with each iteration shifting one element. This shifting operation results in a time complexity of big O of n. Traversal involves visiting each element of the array. This is typically done to perform operations like printing the elements or applying a function to each one. Traversal has a time complexity of O(n), as every element needs to be accessed once. Now that we've covered these fundamental operations, let's connect them to a broader concept, abstract data types, or ADTs. Here, abstract refers to the idea that adds focus on what operations can be performed on the data, rather than how these operations are implemented. It hides the underlying implementation details and emphasizes the interface or behavior of the data structure. You only need to know the operations an ADTs provides, like inserting or deleting elements, not the specifics of how these operations are carried out internally. The focus is on what operations are available, whether it is arrays, linked list, tree, or something else. An array is a practical example of an abstract data type. It defines a collection of elements and supports several fundamental operations. These operations include access, insertion, deletion, and traversal, all of which are essential for managing and working with arrays effectively. Among these, one of the most powerful features of arrays is their ability to provide constant time access, or big O1, to elements using an index, making this operation very fast. Their simplicity and intuitive structure make them a good starting point for learning about data structures. This straightforwardness helps new programmers grasp the fundamental concepts of data structures. One of the key reasons for this simplicity is the way arrays are stored in memory. Due to contiguous memory allocation, arrays are cache-friendly. This means that accessing array elements is likely to benefit from spatial locality. This leads to better performance in many cases, as the CPU can access the data more efficiently. However, arrays do have drawbacks. Their fixed size can be limiting if you need a data structure that can grow or shrink dynamically. Insertion and deletion operations can be inefficient, requiring shifting elements. This shifting results in higher time complexity, making these operations more costly. In summary, arrays are a fundamental data structure that offers simplicity, efficient access, and organized data storage. Their strengths lie in their straightforward nature and quick retrieval times. However, they come with trade-offs, such as a fixed size and less flexibility in operations like insertion and deletion. As we conclude our look at arrays, it's important to note their strengths and limitations. Next, we'll explore the stack, a dynamic data structure that addresses some of the challenges arrays face with its last-in, first-out approach. Stay tuned to see how stacks build on and extend the concepts we've covered, adding new dimensions to our understanding of data structures. Stay curious and keep exploring. Happy coding!